Hello everyone. In today's video, we will determine an unknown resistance using Carey Foster's bridge, and we will be using a virtual platform for performing this experiment. And along with the experiment that we will be performing in the virtual laboratory, I have also added a complete theoretical guidance for you all so that you can understand the theory of this experiment better and can perform the experiment very easily. The theory that I am going to discuss will also help you during your Viva VC in your examination. So without wasting any time, let's begin. So the first thing which comes to our mind is that on which principle does the Carey Foster's bridge work? Carey Foster's bridge works on the same principle of Wheatstone bridge. Now, do you remember the Wheatstone bridge? If no, let me remind you. Here you can see the circuit diagram of a Wheatstone. Let us try to identify all the components. As you can see, this is a power source or a battery. There are four different resistances, namely P, Q, R and S, joined in the circuit as shown. Along with all these, we do have a galvanometer connected between the points B and C. Reminding all of you, what is the use of a galvanometer? A galvanometer can sense the presence of current. If it is showing more deflection, it means more current is there. If it is showing less deflection, we will take the inference that the current is small. However, galvanometer cannot measure current. If we have to measure current, remember, we will be using an ammeter. Moving forward, this bridge is said to be in a balanced condition when the ratio of P by Q is exactly equal to the ratio of R by S. And in this situation, when P by Q is equal to R by S, the galvanometer shows zero deflection, which means no current flows between the points, or you can say that the potential difference between these is zero. And in this scenario, suppose we are designing the bridge in such a manner, P and Q we have chosen to be same, so they are already balanced. In case we know what is this R, we can calculate what is the value of X, isn't it? So using the Wheatstone bridge principle, an unknown resistance can be determined. However, there is a very big disadvantage of this principle. As you can see, P, Q, R and S, these are all single valued resistances. So I can only calculate the unknown value R when I have a unique value of R to be determined. Otherwise, this bridge can never be balanced. This disadvantage is actually overcome with the help of the Carey Foster. We use the same principle of Wheatstone bridge, but we take it to a higher version. Now let me explain to you that how is this principle used in the Carey Foster's bridge. Let me show you the circuit diagram of the Carey Foster's bridge first. As you all can see that the circuit diagram consists of basically a meter bridge. As you can see this wire EF, this is a 1 meter long wire of the meter bridge. This entire bridge that you can see over here is the Carey Foster bridge, which consists of a 1 meter long wire and 4 gaps. Can you identify these 4 gaps? In these 4 gaps, see over here what we have done. We have connected 4 different values of resistance, namely P, Q, X and Y. Next, what I would like to do is to show you the Wheatstone bridge once again. And let us try to now understand that how is this Wheatstone bridge principle analogously working in the Carey Foster's bridge. So if the principle P by Q is equal to R by S is also followed in this Carey Foster's bridge, we have to now identify that who is P, Q, R and S on our Carey Foster's bridge. So let's begin. Now, as you can see, this P and Q on the Carey Foster's bridge are same as P and Q on our Wheatstone bridge. However, who is equivalent to R and who is equivalent to S? See carefully. Over here, between the point B and D is the galvanometer. Same thing can be identified on the Carey Foster's bridge as well. But in between this B and D, if you carefully look at the position of D over here, this point has been shown with an arrow. What does this mean? It means that this is not a fixed point. This is actually the head of a jockey. Means we can move this particular jockey point anywhere between this 1 meter long wire. And whenever the jockey is at a certain point and we get the galvanometer showing a zero deflection, determine or we draw the inference that that is the balanced condition of the Carey Foster bridge. In this scenario, let us assume that this galvanometer is showing zero deflection when the jockey is at this point D, at a certain point D. Then what will be equivalent to the R on the Wheatstone bridge? Value of this R will be nothing but the resistance X in the gap number 1 plus the resistance of the wire of length ED. Are you following me? If you see carefully, this X and ED, they are connected in series. So their resistances will be added up together. And this will form the third arm R of the Wheatstone bridge. Repeating once again, the R of the Wheatstone bridge is actually the combination or the addition of resistances X plus the resistance of the wire of length D. Analogously, who will be this X? S. This S will be the Y resistance plus the resistance of the wire of length DF. From this point D to F, whatever is the resistance of this part of the wire, that we can add with the resistance Y, and that will form the fourth arm of the Wheatstone bridge. In this scenario, we can write that P by Q on the Carey Foster bridge is equal to X plus rho into L1. Now you might be wondering, who is this L1 and what is this rho? This L1 is nothing but the length of ED. Then, how do I calculate what is the resistance of this length of wire ED? The rho that you can see over here is actually the resistance per unit length of the meter bridge wire. Resistance per unit length of the wire when multiplied with the length of the wire will give me the resistance of that part of the wire. Now, if the length of ED is L1 and I am multiplying it with the resistance per unit length rho, what am I getting? I am getting the resistance of the wire ED. And that when added with X becomes the third arm or R. Similarly, what will be this S? It will be Y plus the resistance of this part of the wire. And how much is that? Again, rho into 100 minus L1. Since D is L1 and EF is 100, DF would be 100 minus L1. So, using this particular fundamental, we can formulate the equation number 1. Moving forward, at this point, let us assume that the unknown resistance is the resistance X. Then how can we determine it? Look into the formula once again. P by Q is at our will because we can design the circuit in such a manner that P and Q are equal. We can experimentally determine the value of L1 by moving the value or the position of the jockey and get a null position. And in this scenario, if Y is known, we calculate X, isn't it? However, what if rho isn't known? Which means, what if the resistance per unit length of the Carey Foster bridge is unknown? Then how can we calculate X? Because in the same equation, there are two unknown values. In this situation, what we do, we interchange the position of X and Y on the bridge. Remember, where was X? X was in the gap 1, Y was in the gap 4. We will swap the positions. Which means X will now go to gap number 4 and Y will come to gap number 1. And using this setup, once again we will find out the null point. If now the null point is coming at L2, what will the equation look like? It will look like P by Q is equal to y plus rho into L2 by x plus rho into 100 minus L2. Analogous to equation number 1. Now we have equation number 2. Using these two equations now, we can very easily get the value of rho, which is equal to y minus x by L2 minus L1. However, the problem still persists. Rho is unknown, x is also unknown. Then how can we determine two unknown values from only one formula or only one equation? Now we have to do some trick. What is that? To find this resistance per unit length rho of the wire, we initially do not attach the unknown resistance X in the bridge. We connect the fourth gap with the help of a copper strip. Since the copper strip has almost no resistance, we can assume that X is equal to 0. So, what does the equation look like now? Rho is equal to y by L2 minus L1. However, during the experiment, if somehow L2 minus L1 is coming out to be negative, the value of rho will come out to be negative, which can never be physically possible. So, instead of writing L2 minus L1, we either write L2 difference L1, or you can also simply write L2 minus L1 modulus or modulus of L2 minus L1. Remember, since rho can never be negative, this denominator also can never be taken as negative. Alright? So this is the working formula for determining the resistance per unit length of the Carey Foster bridge. Once we have determined what is the resistance per unit length of the meter bridge, which is rho, once again, now we can remove the copper strip and put the unknown resistance X in the circuit. In this scenario, since rho is already known, using our equation number 3, we can easily get X is equal to y minus rho into L2 minus L1. So L1, L2, all these can be found out experimentally during the experiment, and by choosing various values of y, we can always perform the experiment and find out the unknown resistance X. So with all this knowledge in our minds, let us now perform the experiment in the virtual laboratory. Once again, we are going to use the virtual laboratory of Amrita Vishwavidyalaya. Alright. So this is where I have brought you to the page of the virtual laboratory where we will perform the experiment. However, this particular experiment in their website is to determine the temperature coefficient of resistance, as you all can see over here. Now, in our syllabus, we do not require to perform this part of the experiment. However, the setup that they have already provided for doing the temperature coefficient of resistance is same as what we need for our unknown resistance determination using Carey Foster bridge. So, I have chosen this particular platform to perform our desired experiment. Okay. So, as you all can see here, our experimental apparatus is lying on the table. This thing that you can see is nothing but the meter bridge, as I have already discussed. This one is the meter long wire, or 100 centimeters. This point, as you can see, is the jockey point, and this is the galvanometer, which is already connected. However, the other parts of the circuit have to be completed by us. Trust me, when you will do this on your own, this will be very, very fun. Let us try to complete the circuit first. So, as we know that we have to first determine the unknown resistance, or rather the resistance per unit length of the meter bridge wire. We will not be using a resistor in the circuit now. We will be using the copper strip. and the copper strip will be connected to the first gap. See, I have just taken from here and I have dragged and kept it over here and it has got connected. Okay. Now, just let me show you once again. This was the first gap. This was the second. This is the third gap and this is the fourth gap. These are now empty and we are going to put the components of circuit accordingly to complete the circuit. Okay. So now as we know, we have to attach P and Q over here. We can do with the help of this resistor. So let us drag and drop it. See, the moment you bring it over here, the circuit gets completed. Once again, we need a Q, dragging it twice and putting it over here. So this is P, this is Q, this is the copper strip. Now we have to fill the fourth gap. This we are going to do with the help of a fractional resistor. So I will take this and put it over here. Alright. So with these already put in the circuit, we have to now apply the battery. Otherwise, the entire setup will not be complete. So I take the battery and then I will complete the circuit. And now our circuit is complete. The moment you can see this continue button over here, you know that your circuit has been completed. So we will continue. In this scenario, see the values of the resistance box is seen in front of us, which is now 0. So we have to first choose these values to some finite value. When you click on this, you will be able to see various values which you can choose on your own will. Let us perform this experiment for 0.5 ohms. Now since P by Q is equal to R by S formula or the funda has to be used, remember that P and Q have to be chosen with the same value. So we have set the value of P and Q with 0.5 ohms. Alright. Now it is time for us to choose our Y. Right. So again, I will click on this and let me do it for 0.5 ohms only. So now I have set the value of Y as 0.5. The moment I have put all these things, you can see that the galvanometer is showing me some current. In this case, this is not an analog galvanometer. This is actually a digital galvanometer and it is showing me some value. But what do I need? I need a zero deflection for balancing the bridge. So what we have to do? We have to move the jockey position, right? So using this slider, you have to move it. Now see, the moment I started to move this, the value of the readings on the galvanometer is changing. We have to slide it till we reach the value of 0, which I am trying to reach. Now see, the moment I have crossed a certain value, the values have gone to minus, which means I have already left my 0. When you are very close to these kind of values, I would suggest that instead of using the mouse, use your arrow keys, which I am doing right now to reach to as close possible to 0. Now see, when I was here, it was showing me minus 0.2, whereas slightly different position is 0.0767. So this is the closest I can reach to 0, which means this is my null condition of the galvanometer. What is the length of the wire now? The length of the wire is 56.1. This I can note down. Now, before we note this down, let me show you the table of the experiment that I have already prepared in the Excel sheet. Here. To see what I have done. These are the values of Y and position of null point with copper strip in gap 1 or gap 4. Remember in the theory I had told you that we have to interchange the positions. So once we will find out the null point while the copper strip is in the gap 1 and then we will do it for when the copper strip is in gap 4. So that those will give us the values of corresponding L1 and L2. Since I have already done the experiment earlier, I already have a table filled with data. Right. So let us go back to the setup once again. So once we are ready with our table and we have already found the first null point, we will write down this 56.1 in our table. But remember, where is the copper strip now? The copper strip is in gap number 1. So, in my table, when the copper strip is in gap number 1, you will be putting on these values. Correct? So, like this, you can note down the particular value that you have taken. Moving forward, we have to now reverse the connection. When you press this reverse connection button, you see that the position of the copper strip and the resistor has changed, have been swapped. Once again, we will move the jockey position and determine the null point. Close to 0, I would suggest once again to use the arrow keys. Minus 0.07, right, 0.2. So, this is as close I can reach to 0. In this case, my value of L2 will be 43.9. Once again, I'll take this value and I will note it down in my table. Alright, so this is how you can find out the value of L2 minus L1, and from there you can calculate the value of rho. As you can see over here, rho is equal to Y by L2 minus L1. Same as we had discussed in our theory. Like this, we can repeat the experiment for a different value of resistor. Isn't it? So let us again go back to our old setup. Now we can click over here and now you can change the value of the resistance. So now we are doing it for 0.7 values. 0.7 ohms. Once again, you can change the jockey position and receive a null point and note down the value of your L1 or L2 depending on where the copper strip is. So in this case, it is 58.6. As you can see over here, you will be able to see the numeral of the length. Like this, once you have taken for left gap, now reverse the condition and now find out the right gap once again by changing the jockey position and getting the zero deflection or null reading in the galvanometer. Like so, isn't it? Here you see, we are very close to 0 and this 41.4 in this case will be my reading. Once again, I take this value and I will put it in my table. And like this, we can calculate the value of resistance per unit length for as many readings as we want. And once we have taken say 4 or 5 such readings, we can find out the average. That will be the result of the resistance per unit length of the meter bridge wire or rho of the wire. And with the value of rho in our hands, now we can move forward and to the next part of the experiment where we will be determining the unknown resistance. So let's move forward. Once this part is done, we will reset the entire experimental setup. Press the reset button over here. And you will see once again we are having a fresh circuit to be made. But now remember, since we have already found out the resistance per unit length or rho of this meter bridge wire, we do not need the copper strip anymore. Instead, we are going to use this unknown resistor in the circuit. The rest of the things will remain the same. So let us connect the resistor P and Q. Fractional resistance box over here. Unknown resistance over here. Now students, while I was doing it earlier also, I have seen that this unknown resistor is a bit difficult to drag and drop. You have to be very careful while you are dragging and dropping this. Now do not be afraid when you look something boiling over here. This is just actually the setup. I remember I told you that this was for the temperature coefficient of resistance. Since we are not doing this part of the experiment, we no need to bother about it right now. We can consider this just as an unknown resistance. Alright. Now that all the components have been put to their respective places, you will see once again that the continue button has been activated. Let us move forward. Once again, we have to first set the value of the small resistances P and Q. So let us again do it for 0.5 ohms. So we have set it, and now we have to choose the particular resistance. Over here we have been given the choice of resistance 1, resistance 2. Whichever is your wish, you can choose. With this resistor length also can be varied. Remember, the resistance of a particular length or wire does depend on the length. So let us choose the maximum only, say 25 centimeters. The diameter also can be varied. Whatever is your wish, let it be small only. Because remember, smaller is the diameter, higher will be the resistance. So let us keep it like this. But we are not going to work with the temperature because we are not doing the temperature coefficient. So we will keep it at 25 degrees. This only. Only what we have to do is to move the jockey position as we were doing earlier also. Now let us first choose the value of the fractional resistance. Now remember, over here there are 3 different options. Either it could be fractional or some small value or some large value. Okay, now remember, P by Q is equal to R by S. The entire principle of either Carey Foster bridge or Wheatstone bridge is to balance the bridge. Remember, we have chosen P and Q with 0.5 ohms. Now, it won't be feasible that if I am trying to do or design the entire circuit now with a 5000 ohms things for R and S. So, we will choose almost similar values or at least comparable values. So, let us go to this small part and say I am doing this for 2 ohms. Okay. So, I have chosen the value of this to 2 ohms. Now, what we will do? Once again, we will move the jockey position and try to reach as close to 0 or null. Now that I have come very near to 2.8, now I will move this with the help of my arrow keys. And see, minus 0.18, 0.024. So this is the closest I can reach to 0. And in this scenario, my length reading is 74.7. So let me show you the next part of the table. This. Alright, so here you can write down the value. Now see, let me show you something. Over here, this is gap 1, this is gap 4, and the unknown resistance is in gap 1. So, if the unknown resistance is in gap 1 and the null has been produced at 74.7, what do we do? At gap 1, we will write down 74.5. What was the value? 74.7. Sorry, 74.7. Once this is done, we can get back to doing the reverse connection. Which means now they have been swapped. Once again, we will move the jockey position and try to come to the null. Here we are very close to 0. That's all. So 25.3. So when I take this value and I put it over here, 25.3, I can get my L2 minus L1 and I can get the value of the particular unknown resistance. In this scenario, the unknown resistance is coming out to be 1 point something, isn't it? Once again, let us repeat the experiment for some other value of. So, we will again go back to the original condition and say change this value to 3 ohms. Alright, change the jockey position, come to 0. Note down the value. Where is the 0? Here we are. 0.021 can be the minimum. So 87.2. So once again, let me put down 87.2. Acha, by the way, earlier we had done it with 2 ohms. Now we are doing it with 3. 7.2, and doing for the reverse connection and trying to reach the 0. Here we are, 12.8. So I can write it down over here, 12.8. And see, now the resistance, since I have put the value of y a little wrong in the earlier, now we have put all the correct values, and see, the unknown resistance has come out to be something like this. And the average also can be calculated. So if you are doing this experiment for 4 or 5 times with different values of y, you can find out the average of all those 5 values, and you can always find out the resistance in our this particular setup. We have found this out to be 0.018 ohms. Alright. So like this, you all can find out an unknown resistance using the Carey Foster's bridge. I hope all of you have understood the theory well and can perform the experiment now on the virtual platform. So that is all that I have for you in this particular video. Hope to see you all soon with some more helpful videos. Do share this video with your friends whom you think can get benefit from it. So that is all for today. See you all soon. Bye bye.